note taker?
Oh, note taker. I don't have anything.
We have a volunteer note taker. Anybody who has not yet taken notes? No? Anybody? Anybody who has not yet taken notes and would like to take notes? Going once, going twice. Okay. If somebody would like to take notes, we are offering 1.5 additional points for those who have already taken notes. You have one. All right. You have a note taker?
Good.
Again, I said already in the bonus hour, please fill out the course survey and sign it on your personal information on the Fuji website. This is the data sheet. Apparently there's even an app, Fuji app, which can do it. Also very helpful. Thank you.
Okay. So on Sunday, if I remember correctly, we talked about the response of a membrane potential to a white noise. We defined white noise, and what we did was to measure the mean change in the membrane potential as a response. Well, first we talked about the response to a DC current, and then we talked about the response of a passive membrane potential to white noise. And next, what we would like to do is to consider the response of a neuron to the Poisson-like firing of all presynaptic neurons in the network. This is what we would like to do. And the way that we will do it is basically we will approximate the input to the neuron using the DC component, the average component, and a white noise component. This would be the idea. So we will think about the membrane potential as receiving white noise. But this time, the white noise is the result of the activity of all presynaptic neurons. And we will assume that they fire asynchronously. This is what we will do. So how are we going to map the input that the neuron receives from all presynaptic neurons to the white noise story? Well, the instantaneous rate is already written here. The instantaneous rate can be thought, well, is a sum of delta functions. And so thinking about the delta function rather than as a thinking about the delta function as a limit of this kind of an input, we can talk about the DC input, the average input, and we can talk about the correlations. So for T being different from T prime, then clearly, and this is what we did last class, the average of lambda T prime is equal to lambda square. Or lambda is the rate of events. This is a bit more tricky. Lambda T. Well, this is equal to lambda times 1 over delta T. So how are we going to take the limit of delta T going to infinity? So what would be the value of this term? Okay. So what does it mean? Who said delta? Why delta? Why delta and not 2 delta? Well, delta is a good... I mean, you said infinity, which is a correct answer but not a very useful one. You said delta, which is consistent with infinity, but also 2 delta is consistent with infinity. So how are we going to think about this correlation? Number is like 7 being a number, or we need an answer. We need to map this input to the white noise scenario. Now, some of you have already guessed that delta should be involved. Well, delta should be involved because, well, we go to infinity. As you notice, as delta t goes to 0, this term goes to infinity. And delta even has the right, delta function has the right units of 1 over time. But why should it be delta function rather than 2 delta functions, or 7 delta functions, or pi delta functions? Well, it does matter in the sense that, thinking about the white noise, you could say that we don't care about the variance of the white noise, which is absolutely, doesn't make any sense, because the correlations in the measurement potential did depend on the prefactor of the white noise in the correlations. I mean, this is a measure of how large they are. Yes?
Why not just normalize it somehow, just to consistent?
What do you mean by normalize it? There's a number here. There's a right answer. It's not arbitrary. I mean, if I provide you with let's say I have this signal, and I ask you to compute the autocorrelation, you'll get an answer. There will be a number. There will be a function of, I don't know, ask you about, this is x of t. This is t. And I ask you, what is the value of x of t? X of t prime, it will be equal to something. There's no... So similarly, if we're talking about instantaneous rate, we can do exactly the same thing and we'll get an answer. Now, I understand that the infinite thing is a kind of confusing, but still. So what do we do when we encounter infinity? Well, first we are unhappy. But after getting over the sorrow, we understand that this is only a limit. So the reason why we got infinity here is because, well, we take delta t to the limit. So let's do it without taking the limit. So let's consider this signal. So what would be the correlation function? How would it look like? I'm sorry? So we want to compute lambda t prime. So how are we going to do it? Well, this we did taking the limit of t, delta t going to 0. Okay, so the way to think about it is now to consider lambda t prime average. So one limit that is easy would be when t minus t prime difference is larger than delta t. What would be the answer in that case? Well, this would be this case, right? So independent. So this would just give us lambda squared. So how will lambda t prime look like when the difference between t and t prime is smaller than delta t? So let's say that it's equal to half delta t. So we'll have a signal that looks like this. Let's put it here. So this is our delta t. And this would be the second. This would be the second signal. This would be lambda t. And this would be lambda t prime. So in some cases, if we look at this point in time, this would behave exactly like this one, lambda t, lambda t. In some other... At this point, if we just look at this t and look at these two examples, they overlap. So the value would be 1 over... but for other points, there will not be an overlap. So if we look at the correlation function, so this would be t minus t prime. So when t minus t prime is equal to 0, what would be the height? The height of this correlation function would be lambda times 1 over delta t. Right? When t minus t prime is equal to delta t, what would be the correlation? Now we will go to the value which is, it will go to 0. Let's talk about delta lambda. It's easier to think about it. So the area under the correlation function is exactly 1 times lambda. So this is why lambda t prime is equal to lambda square plus lambda delta t minus t prime, taking the limit. Because the area under the correlation function is exactly lambda. That's why it's delta and not 7 delta or pi times delta. So you said infinity, you were right, but it's a special kind of infinity. You said delta function, you were right, but this is explanation of why it's 1 delta function rather than 7 delta functions. Okay, questions? So now we more or less know how to go from the presynaptic input, which is Poisson-like, and study the effect on the postsynaptic neuron. So let's do it. So we even have our RC circuit. So we consider a single neuron that receives input. So the input to this neuron, I of t, is equal to sum over the spikes of equal to the instantaneous rate, where this is input coming from all neurons in the network. And so the question, we'll start by asking the question, what would be the effect of a single presynaptic action potential? How will a single presynaptic action potential affect the membrane potential of a neuron? So how are we going to do it?
Do we have like a transformation function?
I'm sorry?
Like a function that makes the action potential to what it should be?
So we have an equation for the passive membrane. Tau v dot is equal to minus v plus IR, right?
Yeah, but this I should be like I what it is for action.
Right. So what would be the effect of a single action potential on the membrane potential? Well, from this equation.
What is the I per action potential?
Why do you find this question difficult?
Spikes are not passive.
Spikes?
I mean, what you ask. I mean, here you count spikes.
This is a sum of delta functions on the times of a presynaptic action potential.
Count spikes.
Okay, now ask the question. Let's assume that there's only a single action presynaptic action potential. How will it affect the membrane? By how much? You have an equation here, according to the equation. Yes? There will be a jump of almost R. There will be a jump of R. Let's call this effect of a single presynaptic action potential. And I will denote it by delta V, the change in the membrane potential, which will be equal to what? R over tau. Why is it true? Well, divide the left and right hand side of this equation by tau and integrate over one delta function. This is kind of weird, no? These are units of resistance, and these are units of time. And we're interested in units of membrane potential. What?
The change takes some time.
So in fact, the input is not a sum of delta functions. There is a prefactor that has the right units to correct it, which will take into account things like, there is the width, the time of the event, the correlation, if you like, of the synaptic current, or synaptic conductance, and the change in conductance, the magnitude of the change in conductance. So this is the effect. What would be a typical number? Let's call this V. Let's call this the EPSP.
Can you explain K again?
So, yes. So, I started by writing the input coming from all presynaptic neurons as a sum of delta functions. This is clearly wrong. Why is it wrong? Well, just looking at the units doesn't make any sense. Because the units of the input are, if it's just sum of delta functions, this is 1 over time. And we're interested in units of, well, current. And what we were, the reason why we got the units wrong is that we didn't take into account the fact that there's a prefactor that, as Lior said, incorporates the width of the activation of the synapse. So some time, it takes a few milliseconds, maybe 2 milliseconds, depending on the synapse. And the second thing is the magnitude of the change. The opening of ionic channels. You can open 1 channel, you can open 7. So we need a prefactor, and this prefactor actually has all these units that we are missing. But going back to biology, what would be an approximate size of an EPSP in the cortex? 1 microvolt, 1 millivolt, 1 volt, 1 millivolt. So, well, it depends. The larger ones are close to 1 millivolt, even can be even larger than 1 millivolt. The smaller ones would be something of the order of, 0.1 millivolts. But this is the order of magnitude of an EPSP. Okay. This? Well, you just integrate over a delta function times k. Integrate this equation. Okay, so let's say that this is the input. What would be the average input? Well, the average input would be just equal to k times the average over the sum of delta functions, which would be k times lambda. So what is the expected change in membrane potential due to the average input, due to the DC component, if you like? So let's say that we replace the input to the neuron with its average. What would be the change? Yeah, I know. So what I wrote is a question. What is the change in the membrane potential due to the DC component, due to this term? Yes.
This 0.5 millivolts, is that the maximal?
No, it's not. You mean the maximal? Yeah. This would be the jump. Yeah, this would be the maximum. So you look at the change. There's like a sharp increase and then a slower decay. This would be the height of this sharp increase. And if you take the delta function approximation, you just get the jump and then you get the decay with the time constant of the membrane. So now I'm playing with the numbers, and I ask a question. Okay, the neuron receives input from many presynaptic neurons. What would be the let's assume that rather than these presynaptic neurons firing Poisson neurons, let's say that the input is constant at the average. The question is, what would be the change in the membrane potential? due to a constant input. So basically V is equal to IR, right? So in that case, average of I times R is just equal to K times lambda. This is I times R. And if we replace Kr with the size of the V EPSP, this would be equal to lambda tau V EPSP. Something like that. So what would be lambda? Taking actual numbers. What's the rate of the presynaptic neurons? What's a rate? What's a standard rate in the cortex? Well, what is this lambda? What's the meaning of this lambda? This is the rate of presynaptic action potentials, average of this. What would be like
2 hertz?
let's say 2 hertz. Okay, fine. So this is 2 hertz. Well, this is 2 hertz for one presynaptic neuron. How many presynaptic neurons do you have in the cortex? Excitatory, let's say. How many inputs does the cortical neuron receive?
10,000.
Let's say 10,000. How many of them are excitatory? 80%. So let's say, I don't know, let's say that lambda, so if we take 2 hertz and 8,000 presynaptic inputs, this would be, lambda would be 16, let's say 16 kilohertz. So just for the, so that I will not have to deal with difficult numbers, I'll write here 10,000. So this would correspond to maybe, I don't know, 10,000 inputs at 1 hertz. What is tau? What's the tau? What's the membrane time? What's a reasonable number to take? I'm sorry? More than that. I'd say between 10 and 100. Let's say, for the sake of argument, that this would be let's say 20 milliseconds. So 20 milliseconds is 0.02 seconds. So if we take these numbers, what would be the IR? What would be the change in the membrane? So this is 10,000 times 0.02 times 0.5. So 100 millivolts maybe. So this implies that a steady state input is much, much larger than what would be like a threshold for a neuron. What would be the threshold of how much? Minus 40 is minus 50. So what would be the change? What would be the change? Let's say 20, maybe 15 millivolts. So we're way, way, way above the threshold. So the input is a strong input. So this implies that the firing rate of the neuron is expected to be of the order of tau, of the tau of the membrane, 1 over tau of the membrane, which is like, I don't know, maybe 50 hertz, much higher than the rate that we typically observe in the cortex. Well, it's kind of a problem.
So maybe we shouldn't assume that all the presynaptic neurons
Well, we don't assume that they fire at the same time. We assume that they fire Poisson-like in an asynchronous way. This is what we assumed here. No, they don't fire at the same time. They fire asynchronously.
But we are assuming that input rate.
I'm sorry?
No, I'm trying to realize to understand where we went wrong.
Well, nothing went wrong. We just put these numbers and we got a result that doesn't make much sense from a biological point of view. So there are two issues, okay? One, if we make these assumptions, and just consider the mean input, the result would be that neurons should fire at a too high firing rate, and they should fire regularly, which is inconsistent with the assumption that we made previously. So there are two issues that we need to resolve here. One is the fact that the firing rate is too high, and second is that the firing is expected to be regular because the response of a neuron to a constant input is, well, regular, at least in our model. So something is wrong here. Well, maybe there is a way out, okay? So we only considered the mean input. So actually we didn't take into account the fluctuations. So maybe the fluctuations are so large that the mean is not important. You're with me? But now we have the tools to compute the magnitude of the fluctuations. Right? What tool? The white noise, we computed the fluctuation, the memory potential in response to white noise. So we can think about this input as white noise. It has zero correlations because these are just sums of delta functions. So there are no correlations here. So we can think about it as white noise. So let's look at the, so we can talk about IT prime. Or perhaps it would be more useful to talk about delta IT prime, the correlation in the fluctuations. So this would be just equal to k squared delta of t minus t prime. This is what we did previously here. And now we can use the results from last week and talk about delta vt prime. And just copying the calculation from Sunday, this will be equal to this term, where this is just a sigma square. This is this term that we had previously, and this is equal to k squared r squared lambda over 2,000, the lambda missing here. Which is also equal to V EPSP squared lambda tau over 2. So this would be the variance in the fluctuations in memory potential in this model. Sorry, I'm taking the zero correlation times zero. This would be the magnitude of the fluctuations in the memory potential. So all I did here was just to copy the results from last week and replace a sigma squared tau correlation with a k squared. So what would be the magnitude of fluctuations relative to the mean? So we can think about the delta v squared of delta v squared over this change, the DC change. Let's define it as delta v DC. So just putting the numbers, this will be equal to 1 over square root of 2 lambda tau. So we can put numbers again. So let's say we said that lambda is 10,000 and tau is 0.02. So this would be equal, if we put these numbers, this would be equal to 1 over 20. So the magnitude of the fluctuation is around 5% of the mean. So the fluctuations are rather small. So if the DC will result in a change of 100 millivolts, then the change will not be 100 millivolts, it will be something between, I don't know, 95 and 105. So this did not solve our problem. So we have small fluctuations. So we have a problem. There's something wrong either with our models or with our brains. But the results seem inconsistent.
Is the assumption that it's constant?
Which assumption is problematic?
Constant, the first one. The first one that you asked for.
Stop me. This equation?
Yes.
Well, I didn't assume that it's constant. This is the input that I incorporated. So this input has two components. There is a DC component, and there are fluctuations. These fluctuations, which I took from the data. So the input has a DC component and fluctuation. So the effect of the DC component on a passive membrane will be this change in potential. If you incorporate the fluctuations, you expect to see plus minus 5 millivolts. Yes?
What about the fact that we just neglected V dot?
I didn't neglect V dot. This is how, when computing the fluctuations, I took into account the dynamics of V. This is what we did last week or last class when we computed the effect of white noise on the moment potential.
Yeah, but you didn't consider it when you
Here?
computed the.
Of course I did.
The average of I.
No, of course I did. Well, you take the limit. I mean, you look at the steady state change. Okay, so what we'll have basically, you are right that if we incorporate the threshold here, what we will get is a neuron that receives a relatively strong input. Whenever it crosses the threshold, it fires an action potential. But we expect that the firing rate of the neuron will be much larger than the firing rate of the presynaptic neurons in the network, taking these numbers. And we expect that the firing rate would be regular, and both are inconsistent with what we measure. So clearly there is something that we are missing.
I don't know if it's correct. So we mentioned something like flying together, running together. So do you think the presynaptic input is really random? So probably, I think it's no really the possible distribution.
Well, still, if you have some neurons that are, so you think that some neurons receive stronger inputs and some neurons receive weaker inputs.
I mean, some neurons they fire together. Some neurons they fire together.
Well, when you look at the recordings, they're pretty asynchronous. I mean, you are right about when people measure these correlations, it depends on the lab, but it will range between, I don't know, 0.01 and 0.1, maybe 0.2. But the correlations are weak. Neurons to first approximation are asynchronous. So we have a problem, yes. We're missing something.
Just a question about something I didn't see.
Okay.
I is telling me something about action potential in the presynaptic
Right.
neurons, right? And the way I know it works, it's not like it would go directly to an external. There's an intermediate synaptic chemical transfer
Well, this is a all this is here.
But how, I just don't see how it is.
Well,
How it is transmitted. I mean, how can you see it mathematically that it is transmitted?
well, I'm telling you that if you look at EPSPs, the magnitude of EPSPs is on the order of half a millivolt. So this will incorporate the entire chemical machinery. Yeah. So there are two issues. Okay, so one is, there are two issues here that I would like to emphasize. One is that we get a too strong input to the firing rate that we typically, sorry, that's one problem. And so one interpretation, one thing that one could say is that maybe we got the numbers wrong. Okay, maybe there's something wrong with the numbers. Maybe it's not 10,000, it is just, I don't know, 5,000. Maybe we shouldn't take this as 0.5, maybe it should be 0.1. And maybe tau should not be 20 millisecond, maybe it should be a smaller number. So maybe something, all these numbers are inflated, and if we take the true numbers, then we will become sub-threshold. So maybe, that's one interpretation. But clearly this cannot be right. Something is wrong here. Something is very wrong in our model, and we need to understand what. Yes?
What is the effect of the reset period on
Well, the reset would be like 1-2 milliseconds, maybe 3 milliseconds. It will not have a large effect, at least when you talk about the firing rate. So actually thinking about it in the first place, if we think about neurons whose membrane time constant is let's say 10 milliseconds, just in order of magnitude estimation, we would expect that the neurons would fire at a firing rate which is on the order of 1 over the tau of the membrane potential. That would be like a standard, unless we do some fine-tuning. So the firing rate of the neurons is way, way too low. So there's a puzzle here. So we'll take a break, and after the break, we will consider the solution to this puzzle.
שאני לא מהתחום, מה כל דבר כאן אומר? לגבי טאו?
טאו זה membrane time constant.
שזה אומר כמה זמן צריך לעשות שינוי כאילו בפוטנציאל?
במעגל הארצי זה דבר הזה.
זה הזמן של הקיבול.
זה מסתכל על המספרים, אז זה
שנייה, ביולוגית אבל זה אומר שכמה זמן לוקח להיטען
יש פה גם קיבול וגם איכות.
אוקיי. זה כל מה שאמרנו עם הפאמפי כאילו של ולמדה?
למדה זה קצב הירי.
זה קצב הירי.
ירי הפרסינפטי. עכשיו כל נוירון מקבל אינפוט לא אתה מסתכל על, אילו הנוירון היה מקבל אינפוט מנוירון אחד פרסינפטי, קצב הלמדה היה נגיד שני הרץ. כל נוירון מקבל אינפוט מ-5,000, 10,000 את הלמדה, זה הסכום על האירועים האלה שקוראים בצד הפרסינפטי. זה הרבה. אתה יודע ש100 מיליוולט זה בטח מאוד מאוד גבוה? 100 מיליוולט אומר שמהר מאוד בעצם, בחישוב אתה תקבל שמהר מאוד אתה חוצה את הסף, אתה חוצה את הפעולה, שוב אתה חוזר חזרה. שמה זה הסף? 15 מיליוולט, 20 מיליוולט. אתה מהר מאוד מגיע לשם. מה זה מהר מאוד? זה order of time scale of tau. אתה מצפה שיהיה לך א' ירי בקצב שהוא סדר גודל שהוא חסר תאו. ב' הוא צריך להיות רגולרי. אתה מגיע לסף, אתה לא רואה את זה.
יש הקורלציה, יש ביניהם 1/20.
זה אומר שהפלוקטואציות לא משקיעות.
למה זה משקיע?
אוקיי. אפילו החישוב שעשינו חישוב לממוצע הוא נראה חשוב סביר.
אני לא הבנתי, כשאתה מדבר על שינוי במתח, שינוי בכמה זמן. כי יש לזה...
זה מדבר המקסימום. יש שני שלבים, יש עלייה מהירה וירידה. עלייה מהירה היא בעצם נובעת מזה שהסינפסה היא לא... יש לה זמן סינפסי, ואז יש לך ירידה שנובעת מהטאו ממברן. אני מחליף את זה בסמטה דלטה, זאת אומרת, עלייה אינסטנטנית כבר יש לך ירידה. ולוקח נגיד סדר גודל שמה, סדר גודל שמה.
אז כאילו נגיד, אמרת שבאמת אנחנו עושים אינטגרל פעמיים בעצם?
לא, פעם אחת.
ממה, כאילו?
אינטגרל, תחשבי שבצורה הכי פשוטה לחשוב על זה, שבאינסטנטניוס טיים הגודל הזה הוא V, ופה יש לך גודל שהוא אינסוף. זה לא דבר דומיננטי. בעצם, כשאתה עושה אינטגרל על דלטה, אתה מקבל קפיצה. מה זה אינטגרל על דלטה של T? אינטגרל dt של דלטה של T. נגיד מינוס אינסוף. איך זה ייראה? כל עוד את קטנה מאפס, אז זה אפס. כאן, אינטגרל על דלטה הוא אחד. אז לקחת את הקפיצה הזאת, זו קפיצה במתח, ואז לך D1, כמו שעל שזה מגלל, בגלל מינוס D. בצורה אחת, תסתכל על המשוואה.
לא הבנתי בדיוק מה אתה עושה, כאילו אתה רוצה...
אני מכניס את ה-I הזה של T לכאן, אני קודם כל מכניס נוירון אחד, פוטנציאל פעולה אחד פרסינפטי. אז אני אומר לך, זה יגרום לקפיצה במתח, עושה בירידה. מה יהיה גודל הקפיצה במתח? גודל הקפיצה במתח יהיה R חלקי תאו כפול K. זה מהמשוואה המתמטית. שנייה אחת, זה מהמשוואה המתמטית. בביולוגיה אני יודע שזה בערך חצי מילימטר.
עכשיו אני אומרת ש-I שלי הוא בעצם זה פונקציה, אז אני מגובה פה לדעת, נכון? ואז על מה יותר במשוואה?
פתרנו את השאלה, שוב פתרנו משוואה. תציבי דלטה בפתרון. זה יש נמצא לך קפיצה.
J.I. והכל, חלקה קורה שמירון אחד כמה נורון את הקשור בפרק זמן של טיסה על מיוסטי. צריך לעשות ככה הוא חשוב לפתח נכון?
מה הסבירות שאפשר לעשות? זה הרגע האחרון. זה הרגע הכי פחות נראה לי.
כל הבירות. אבל יש לנו משהו הקודם, אני חושב.
אם אתה מכיר, זה כאן זה אפס. זה
נכון, כי יש לך מה? יש לך את הדבר הזה, כן? הדבר הזה כפול כן? כאן זה לא כאן זה לא זה זה אז מן הסתם תהיה יהיה לך איפשהו, רק ששניהם יחלפו אחד השני כן? עכשיו זו פונקציה של דלתה T נראית ככה, כן? פונקציה של המרחק בין ה-T נראית ככה בדיוק דלתה T כן? שזה בדיוק דלתה T הדבר הזה זה דלתה T, כן? ברור שזה דלתה T? הידיעה זה דלתה T וזה דלתה T כן? אז שווה לדלתה T בדיוק, אז זה כאילו מתחיל בדיוק כשזה מסתיים. בזמן הראשון שבו זה 0, וכל מה שהוא קטן מדלתה T, אתה מקבל משהו. כן? אתה מקבל משהו, אתה מקבל איזושהי חפיפה, כן, משהו שונה. כשבדיוק 0, אז אתה מקבל את הלמדה חלקי דלתה T, שזה מצאנו מתישהו כאן, כן?
וזה למה? בגלל שאם ניקח למדה Autocorrelation אותו זמן
פשוט תעשה את תעשה אינטגרציה. לא יודע שלא. זה פשוט הפונקציה, כן? זה פונקציה, זה למדה של זה לא משנה, כן, זה פונקציה. אתה רוצה את זה, אתה לוקח אינטגרל. מה זה בעצם? נכון, שזה שווה לפונקציה. כן, אתה עושה את זה. וכאן יש גם קום על מול K שהוא טימסטיק.
למה הגדרתם שהאלכסון 0 ב-J? למה הגדרתם? אני לא יודע אם זה
זה היה כאילו ל-T כשאני גדול, אני יודע איזור של הדלתתי. זה היה רק באזור של הדלתתי.
אבל לדעתי לא.
אולי כאילו מחוץ פונקציה, הרעיון שלי זה איזושהי פונקציה שתית, ואז לא, אני
Don't ask me to
Do you understand why they get it from how they get it? This one, right?
Yeah, that's great.
How what is the configuration? What's the count?
Divide by tau, then like this one is like your tau.
What's minus? So just consider in the zero.
יונתן? מה? אם אין חפיפה בכלל בין האירועים, אז למה זה לא שווה לי את זה? הקורלציה משנה.
כי יש סיכוי ש... אבל יכול להיות שזה ייפול על זה.
אבל נגמרנו שזה לא יהיה.
כן, אבל זה יכול ליפול על אירוע אחר שהיה. יכול להיות שהספייק הזה ייפול על הספייק הזה. באותו זמן. הסיכוי שזה יקרה זה למדה בריבוע, והגודל של זה זה 1 חלקי דלתה T בריבוע.
למה זה גודל של חלק, נכון? זה חלק בריבוע.
לא, קצב. כל שקל.
שיצא 2 זה למדה בריבוע.
Okay. Okay. We left before the break. You all left the room puzzled, not because of the heat, not because it's summer, but because it's not clear what is wrong with our model. Any ideas? What's missing?
Can you give us a hint?
Yes, I will give you the answer. Well, the hint is that, well, that's the answer, basically. Inhibition. There's inhibition in the brain. It's very important. And we didn't take inhibition into account. So the way to incorporate inhibition, well, would be, well, one way of modeling it. Again, that would be just an approximation, but just to get a feeling, you will have a sequence of events, presynaptic events, but this, with its own K, but this time it will be negative. So if we have inhibition, well, that's good, because inhibition can be as strong as we want. So it can counter this 100 millivolts and give us whatever number.
Why can it be as strong as
Well, in the model. Well, fair. That's no. Bear with me. Okay. So at least it has a potential of solving the problem, right? It has a potential of solving the problem. So let's see what we need. So what do we want from the inhibition? Yes.
Not just opposite to the excitation and just increase your firing rate and all.
Well, let's see what inhibition can do. So let's say that we have inhibition that is exactly, whose mean input will give you minus 100 millivolts. So then the input, the average input of the neuron would be 0. So we will have fluctuations which will be on the order of what? Why 5? So we'll have fluctuations which will be on the order of maybe 5 millivolts, maybe slightly more because there will be some fluctuations from the inhibition, but basically we'll have fluctuations that are way, way below the threshold, and the neuron will not fire at all.
80 millivolts.
Okay, so now we are, who will give me 80 millivolts inhibition. So 80 millivolts is a good idea. Why it's a good idea? Because if we have minus 80 millivolts and 100 minus 80 is 20, we're exactly at the threshold. And then we'll have a firing rate that will be determined by the fluctuations. Maybe, let's say, not 80, let's say 85. Then we'll be slightly below the threshold. And then we can have a firing rate which will be irregular because it will be generated by the fluctuations. And we can, if we are unhappy with the firing rate, we can, let's say the firing rate is too low, we can slightly decrease inhibition or increase excitation somehow, and then we'll get the desired firing rate. What is the problem with the solution? I'm sorry? It will require fine-tuning. So any change, any small change in the input will have, I don't know if to call it catastrophic, but the outcome would be a very large change in the firing rate and properties of the different neurons. So this would imply that the brain should be very, very finely tuned, such that excitation balances inhibition, so that we are in the regime where we are near the threshold and it is the fluctuation that generates the firing rate. But, yes, sorry.
Is this biologically possible? It seems like it is. Because if you think about the epilepsy that everything...
Well, what's the alternative?
I don't know, but I'm asking if it's something reasonable to...
Well, it's something that we definitely dislike as people who study the brain, because it seems that it requires some very fine tuning of the parameters, and also, think about, let's say you move from a dark room to a bright room, and there's large change in the external input, and maybe this would again have catastrophic, well, not catastrophic, but have a huge effect on the firing pattern of the neurons, and this is not something that we see in the experiment. So we are not very happy about this solution. It's a start.
Also, in the scenario that you described, there are a lot of other stations you can modulate in the sound.
I'm sorry? I didn't hear you.
No, I'm just saying that it's not that necessarily the input, in case that there is suddenly very bright light, does the input to the cortex change dramatically, or because there are many stations in between that can...
So maybe there will not be a change, but people, that's an interesting question. If you read the literature and talk about things like working memory, so at least in the old literature you see that median neurons increase their firing rate in response to external input, but like you need to remember something, and if you look at orientation selectivity, you put an orientation, some neurons will increase the firing rate, but it seems that people have not paid enough attention to decrease in the firing rate. So it's more complicated than that, and maybe we will be able to say something about it. But definitely this is a solution. If we accept it, it's a solution that will require some fine-tuning to understand how things are going. But we are here today what we will do now is what I will do now is show you that under certain conditions you will get exactly this solution, that inhibition balances excitation without any fine-tuning. So this would be the outcome of the dynamics of the network. So we can have this solution without any requirements for fine-tuning. This is an interesting result. Yes?
I think you said previously that you're just going to take the same way you define the excitatory input, but just with the neuroscience.
Yes.
Science, and I'm wondering why is it a good model of inhibitions, and like sometimes you see things like shunting, you don't actually get as far as infrared.
That's a good question, but as always, we start with simple, and then you can. I will show you that with this assumption on inhibition, we will get some interesting results. And then the next question would be to say, okay, but also excitation is change in conductance. It's more complicated than that, of course. But we start with the simpler stuff, and okay. again, excitation is not a jump in the potential, and EPSP will depend on the potential of neuron. There are many approximations that we make. Yes?
What about the shunting effect? Like in the Jessup model, when there are two synapses that fire together, so the sum is less than the two of them acting alone. So maybe also here that you have many synapses, excitatory synapses, they act as a shunt and reduce the voltage.
Again, this is a kind of criticism similar to the previous criticism. It could be. I mean, maybe it is a solution, but now it will be your goal to prove that this model will indeed result in the Poisson-like fire. That will indeed result in Poisson-like firing, in asynchronous Poisson-like firing that we see in the cortex. I don't immediately see how this can come about, but maybe you're right. But the point is that you need to tune the inhibition to the excitation. This is a challenge. How do you tune the inhibition to the excitation? And what I will show you now is that this is something that naturally emerges from the dynamics under certain conditions. And this is interesting. Yes?
The tuning emerges?
Yeah, the tuning. Okay. Okay, so we're considering a large network of these integrated fire neurons. So there's a large network of neurons. And can you close the door? Do you mind? Thanks. And each receiving input so there's a network of with a large number of neurons, and each receiving input from a large number of neurons, but from a small subset of the network. Okay, so think about the cortex. Each cortical neuron receives input from, let's say, 10,000 presynaptic neurons, maybe 5,000. But in the network, maybe there could be, I don't know, 10 to the 8 neurons.
So K using then the input to...
The number of presynaptic neurons per postsynaptic neuron. And another assumption that I'm going to make is equal synaptic connections or synaptic strengths. So this is an assumption that we will relax later, if we have time. Questions about the model? Yes.
What do you mean by equal? So,
Synaptic strength.
Or
No, equal. All of them are equal to all.
plus minus something?
All excitatory synapses have exactly the same strength. So we said previously that an EPSP is 0.5 millivolts. It's not 0.5 millivolts, there's a distribution. And rather than taking a distribution, I'm taking a single number.
The number for compensatory and inhibitory?
No, 1%. I'll write equations, and it will be clear. So the dynamic equations are the following. So we have tau vi dot. So this is the change in the moment potential of the ith neuron of a population alpha. There will be excitatory and inhibitory neurons. This will be equal to minus vi alpha plus hi alpha of t, where I goes from 1 to and alpha. This would be the index of the neuron, and alpha is either excitatory or inhibitory. Questions? The back? And the input that the neuron receives, so the input to the neuron, to the ith neuron of population alpha is just equal to sum over all the excitatory neurons, Jij E alpha, lambda J E T. So this is the strength of a connection from the jth excitatory neuron to the alpha, to the ith alpha neuron, times the instantaneous firing rate of the jth excitatory neuron, minus the inhibitory input, which would be sum over J, Jij IE from the inhibitory neurons, lambda J I T, this would be the instantaneous firing rate of the inhibitory neurons, plus H external alpha. So this is the input to the ith neuron of population alpha. Yes?
We have some assumption about the ratio between inhibitory and excitatory?
No.
Is that proportional?
No. Not here. Well, here I'm assuming that each neuron receives, so the sum is sum over all connected neurons. So the number is K. And for the sake of simplicity, I will assume that the number of excitatory inputs is equal to the number of inhibitory inputs. In reality, the ratio is about 2 to 1. So there are each neuron receives something like, I don't know, 6,000 excitatory input from 6,000 excitatory neurons and 3,000 inhibitory neurons. Yes?
Is K a constant number?
Yes, but for the sake of this analysis, yes. Now the assumption of equal synaptic strength implies that Jij alpha beta is equal to the same, is equal. I will write it down and then I will clarify. It is equal to 1 over square root of K times J bar alpha beta. So let's see what I wrote here. So one thing that I wrote, that Jij is equal, so all E to E connections are of the same strength, all E to I connections are of the same strength, of I to E and I to I are of the same strength. This is one thing that I did here. The second is I assume that the strength of a synapse scales like 1 over square root of K, where J bar alpha beta is of order 1. So what are the implications? What are the implications? So let's just consider the excitatory part of the input. So if each neuron receives input from K presynaptic neurons, the strength of each one is 1 over square root of K. Let's say that the firing rate is some kind of order 1. We'll be more precise in a second. Then the strength of excitatory input goes like 1 over square root of K. If K is large, then this implies that the input to the neuron, the excitatory input to the neuron, is very large. And this, in agreement with what we, with the numbers that we had previously, that if we just think of the excitatory input to a pyramidal neuron in the brain, the total excitatory input is relatively large. Put differently, we assume that synapses are strong. Similarly, we assume that the external input is also strong, in the sense that it's equal to square root of k times h external alpha, where h bar external is of order 1. So basically, we have the input to each neuron is very large, or at least it is a sum of 3 numbers, each of them being very large. So, thinking about the tuning problem that we had previously, this is a way of simulating or modeling the tuning problem that we had previously. Questions? Yes.
Maybe it's about the bar notation you're using.
Yeah.
What they mean?
Well, just a way different from, no, it's not average, just to say that it's different from the actual input. If you want a different way of. Okay. So, a second assumption that we're going to make, as we did previously, is we're going to assume asynchronous firing with equal rate. Asynchronous firing rate. Asynchronous firing of neurons with equal rates. So all excitatory neurons basically firing at the same rate. Again, this is an assumption that at the moment is easy to justify, because all neurons receive exactly the same number of inputs, and synaptic strengths are the same. So there's symmetry here between the different neurons in a population. So it makes sense that they will fire. If there's no symmetry breaking here, then they will have all equal rates. So, okay. So now let's with this assumption, let's look at the input to a neuron. So the input to a neuron has 2 components. There is a constant component, which corresponds to the average of this term, plus a time-dependent component, where mu alpha is just equal to the average of this, average over time. So what's the average over time? Well, the average over time of this term would be lambda e. We have k terms like this, multiplied by j alpha e, which is equal to j alpha e, which is equal to 1 over square root of k of j bar alpha e. So this would be equal to, the first term would be equal to square root of k times j bar alpha e times lambda e. This would be the firing rate of excitatory neurons. What would be the second term? Well, we have this. First, we're talking about the average. We're computing the average. So what would be the second term? So there will be minus, well, the same thing, square root of k. So we can put here a parenthesis, square root of k, j bar alpha I lambda I, plus h bar alpha external.
And why is this in the parentheses?
Well, you have the square root of k.
But why is the external
The external input is also strong, also scales like square root of k. Okay, now let's talk about the second term, the time dependent. So this has zero mean, right? That's by construction. So eta I alpha eta j beta average. Okay, so there will be two components here, where there is a case of alpha is being equal to beta and I being equal to j. This would be the autocorrelation. And there will be the case of I being different from j and alpha being different from beta. So let's talk first about the case where alpha is equal to beta and I is equal to j. So what do we have here? So we need to take the autocorrelation of this, right? So how are we going to do it? We're talking about the fluctuations. So the only thing that fluctuates here are the lambdas. So we need to look at delta lambda and delta lambda. And now we need to take the average over the product of these terms at different times. You with me? So we assume that the network is asynchronous, meaning that neurons, the firing of neurons has no correlation. It's like Poisson. So this would mean that the correlation of this term with this term will be 0. So the only component that will, the only contribution would come from the autocorrelation of this with itself and this with itself. So what will we get here? So what will be the contribution from this term? Well, if everything is asynchronous, the correlation of firing rate of one neuron with the other is 0 unless we're looking at the same neuron. And we have a sum of k presynaptic neurons, each one contributing to the variance how much? So we have the j squared. J squared is equal to 1 over k j bar squared. And this would give us lambda times the delta function. We have k such elements. So k will go away. And we are left with j bar squared alpha e squared lambda e up to the delta function. This will be the contribution from this term. And what will be the contribution of this term? The same thing. plus j bar alpha I squared lambda I times delta t minus t prime. So here we have t prime.
You have k in both. One is less than the other, right? Less term.
Here, for the sake of argument, I'm going to assume that each neuron receives exactly k excitatory inputs and exactly k inhibitory inputs. Same number, exactly the same number. In reality, it will be a factor of 2.
Between them.
Yes. Well, in reality, they don't receive exactly k.
That's 80%
No, 80% of the neurons are excitatory and 20% are inhibitory. But if you look at the number of inputs a neuron receives, there's a different number of I to E and E to E connections, such that each neuron receives about 2 to 1. The ratio of excitatory input to inhibitory input is about 2 to 1. 2 excitatory to 1 inhibitory. Well, what about the case of I being I is not alpha is not equal to beta, or I is not equal to j? Well, then there will be no contribution because of the asynchrony assumption and the fact that k is very small, so it's very sparse. So two neurons receive basically inputs that are with no overlap.
What's the community for, except for the asynchrony?
Well, there's no. If I'm looking at the input, let's say that you have a network with 3 neurons, and they're all connected. So the input that neuron number 1 receives is correlated with the input that number 2 receives, because they both receive input from neuron number 3. But if k is very small, it's very sparse, and the probability that the two of us, being 2 neurons, will receive the same input is very small. No, that's because k is much smaller than n.
Oh.
Because k is much smaller than n. Okay, so note that we are in approximately the same place as before. So mu alpha, the average input, is order a square root of k, if we just naively take the numbers. And the fluctuations are order 1, temporal fluctuations order 1. So we are in exactly the same place as before. So naively, we expect to get that behavior will be dominated by this term, in the sense that firing will be at saturation, either 0 or firing at a high rate. So what we are going to do now we don't have much time. I'm going to argue that there exists a range of parameters, a large range of parameters, such that no saturation solution exists. Now, if no saturation solution exists, the implication is that this should be order 1 over square root of k. This should be order 1 over square root of k. This term inside the brackets. Now, if this term is 1 over square root of k, and we take the limit of large k, then we have 2 linear equations. There are 2 things. First, we have 2 linear equations that will determine the firing rates of excitatory and inhibitory neurons. One coming from mu excitatory and one coming from mu inhibitory. And second, we got exactly what we wanted, meaning that excitation and inhibition almost cancel out. Almost, meaning up to a factor of 1 over square root of k, such that the mean input is the same order of magnitude as the fluctuations, which are order 1. I'm going to argue that under certain conditions, or if there is a set of parameters, a large set of parameters, or range of parameters, to be more precise, such that no saturation solution exists.
What do you consider saturation?
Well, lambda being equal to 0 or lambda being very large. Now, lambda will be large if lambda e will be large if mu e is large. So there's no solution. So the only solution that the network can converge to is a solution where this is small as 1 over square root of k, implying a relation between lambda e and lambda I, which will depend on the order 1 terms, these j alpha beta bar.
But isn't it weird that you need all the neurons to all the rates go up together and all the rates go down together? It looks like something that was.
This would be the solution. Actually, you see similar things in the experiments. Excitation and inhibition go together. Okay, so the only thing left to show you is that to find the range of parameters in which there is no saturation solution. This is a naive expectation, assuming that this is order square root of k. So this is what we need to do. Okay, so what kind of solutions can we expect? Saturation solutions. So let's assume one possibility is that the total input is way below the threshold. So this would be dominated, the input to the two populations would be such that they receive a very small input. So one possibility to consider is the case that lambda e and lambda I are both very small. So this would be inconsistent with H external E larger than 0. So if there is an external input to the excitatory population, this solution cannot happen. Why? Because if lambda E and lambda I are equal to 0, then we are left with the external input, and it's sufficient to assume that there is external input such that this is not a solution that the network can converge to. Put differently, if we assume that H external is larger than 0, then this set of equations cannot result in a solution in which all neurons are quiescent in the network. Okay, maybe there is a solution in which all excitatory neurons are quiescent and all inhibitory neurons fire at a very high rate. That's another possibility. So under certain conditions, we may expect to have this, we expect this solution, but if we assume that the external input to the inhibitory population is much smaller than the strength of the I-to-I connectivity, if the external input is not sufficiently large, for example, let's say that there is no inhibitory external input, we will not see this solution. Right? Because, well, the self-inhibition will dominate, and then you will not be able to find a solution which inhibitory neurons are active. As long as this solution requires that the external input to the inhibitory population will be larger than the self-inhibition. Now, if the self-inhibition is, if there's no external, for example, if there's no external input to the inhibitory neuron, then you will not see this solution. Well, a third possibility is that the firing rate of the excitatory neurons is large, but that of the inhibitory neurons is very small. Well, this is inconsistent with I to E, E to I being positive. So if there is E to I connectivity, then this is not a valid solution. A fourth possibility is saturation of both the excitatory and the inhibitory neurons. Now, if the Ji to E is sufficiently large, this is not, we will not be able to find this solution. So, put differently, if under these assumptions on the parameters, there's no saturation solution. And the only solution that emerges is a solution that satisfies these equations, namely JEE bar lambda E minus J I to E bar lambda I plus H bar E external is equal to 0, and we'll have another equation coming from the input to the inhibitory neurons, J E to I times lambda E minus J I lambda I plus H I external is equal to 0. So, under these conditions, the dynamics will converge to a set of rates that is consistent with these equations.
Fourth one is JIE or JEI?
JE to I.
Yeah, no, in the last one.
Sorry, JI to E. So in this case, we get an order 1 firing rate. There's no saturation. There's order 1 firing rate, and this doesn't require any fine tuning, because basically, if you just change these parameters, you'll get a change of the firing rate of the excitatory and inhibitory neurons such that these equations will be satisfied. And the result is, if these equations are satisfied, that the total input to the neurons is very close to the threshold. Now, if it is very close to the threshold, what generates the firing rate are the membrane potential fluctuations. Now, what's the time scale of the membrane potential fluctuation? This would be of the order of tau, of the membrane tau. Now, the total firing rate is much, the spike interval is much longer than the time constant of the membrane. So by the time a neuron fires an action potential, the neuron forgot all its history. So the result would be a distribution of interspike intervals which is exponential, similar to the basketball, similar to the Caesarean sections. So the fact that the firing rate is much lower than the membrane time constant implies that consecutive spikes are approximately independent. Put differently, that the firing pattern is Poisson-like. So now we close the loop. The presynaptic input is Poisson-like. Excitation and inhibition are dynamically balanced such that the firing is driven by fluctuations. The timescale of the fluctuations is much shorter than the interspike interval. As a result, consecutive spikes are approximately independent, and as a result, the neurons fire Poisson-like. And now we have a consistent solution that incorporates the pattern of activity of both the presynaptic neurons and the postsynaptic neurons, and in the network, all neurons are both presynaptic and postsynaptic. Questions? We need to stop here. I'm still unsure about what to do on Sunday, so I'll just take 2 minutes of your time and tell you one more thing, which is kind of interesting. In this analysis, we assume that all neurons receive exactly the same input. Same number of inputs, the same synaptic strength. Now, in real life, there is a distribution of inputs. Some neurons, even by chance, will receive, even if we just draw connections by chance, some neurons will receive slightly stronger input, some will receive slightly weaker input. So there will be this term for each, the mean, the time average term for each neuron will have this component, plus fluctuations, which will also be order 1. And this will result in a distribution of firing rates along the neurons in the network. And it turns out that in the same framework, one can also explain the distribution of firing rates in the cortex, which is approximately log normal. So I may or may not discuss it on Sunday. I don't know. We will see. Questions?